Hello everyone, welcome to my channel. We are on to the next lecture of thermodynamics chapter from class 11, and in today's video we will be talking about enthalpy of reaction, different types of enthalpy of reaction. Okay, now we've already discussed what is enthalpy, and we've already seen that the enthalpy does not, we are not able to calculate the actual value of the enthalpy. We can only measure the change. So we write always delta H. Delta H. We will read the delta H as enthalpy of the reaction or heat of the reaction. And how do we define it? We define as amount of the heat change taking place when quantities mentioned in the balanced chemical equation react completely. Now, to understand that, I have written one equation. Say methane undergoes combustion and it will form carbon dioxide plus water. This much heat change is given. This is given as delta H minus something. Minus means it is exothermic reaction. It is exothermic. This is one way of representing the reaction as exothermic. We will read enthalpy of the reaction is minus this much. Now, what is the exact meaning of the definition? Let us understand that it's a balanced equation. In the balanced equation, what quantities are mentioned? Let's write their masses. This is 16 grams of methane, molecular mass of methane. This is 2 moles of oxygen, that is 2 into 32 grams. When 16 grams of methane react completely with 64 grams of oxygen, what is the heat liberated? That is called as enthalpy of reaction. Now, it's not necessarily always it will be liberated. That is why I wrote here amount of the heat change. Change means it can be endothermic or it can be exothermic. It can be either amount of the heat absorbed or evolved. Anything. When we write change means it can be anything. That depends upon the reaction we are talking about. Like in the present case, we took the example of combustion. So combustion is always a exothermic process. So in that process, energy will be liberated. General aspect, we say, as I told you, we can only measure the change. That means sum of enthalpies of the products minus enthalpies of the reactants. That is called as the enthalpy of the reaction. Okay. That means we can say that the delta H reaction, enthalpy of reaction, we'll write like this. Delta is change, enthalpy, and R here stands for the reaction. That is equal to the sum of. The sum we can write down the products individually. So we can write down as the enthalpy for carbon dioxide, which is in the gaseous state, plus enthalpy twice of, because it is 2 moles given. Twice enthalpy for the water molecule. Okay, that is the reactant part. This minus that of the product. So you will have enthalpy of methane gas plus twice of the enthalpy of oxygen. Okay, that product minus the reactant, whatever value you get, if it comes out to be negative, it will be exothermic reaction. This is one way of representing. Another way is, if we don't write in terms of delta H, we could have written this whole equation as such. Like, let me write here and explain. This plus 2O2, and if you are writing this CO2 and 2H2O, we may write plus 890.4. It is 890 point, it is 0.4 kilojoules per mole. That means we can write this way also. This is there and this much heat is evolved. Either you write as plus heat like this, or in terms of delta H it will be minus. And if we are writing for, and this is for exothermic. If we have to write down for endothermic, it will be reverse. Some reaction endothermic is there, then instead of delta H form minus, we will write there plus, and for endothermic we will write down here minus sign. Here we will write down minus, or on the left hand side we can write down positive heat. It is one and the same thing. So this equation in which the physical states of all the reactants products and the heat changes are specified, these equations are called as thermochemical equations. These are termed as thermochemical equations. Thermochemical equations may, along with the physical states, the heat changes are also given. Fine. Now moving on to the factors affecting the enthalpy of the reaction. The first factor which affects the enthalpy of the reaction is the quantity of reactant. Means if I am saying 16 grams of methane is reacting with 64 grams of oxygen, the heat liberated is say 890.4 kilojoules per mole. Suppose I double this amount. I take suppose say 32 grams of methane and I'm making it react with twice of 64 grams of oxygen. Then what will be the heat liberated? It will be twice of that. It will be 2 into minus 890.4. Means whatever changes you make to the quantities mentioned, the heat changes also will be changing accordingly. If you half the amounts, then the heat also will be half. If you double it, make it 4 times, accordingly the delta H value will change. Clear? Then the physical state of the reactants and the products, that also will decide what will be the delta H value. Now maybe some reactants are there in the solid state or liquid state or the gas state, then accordingly the delta H value will change. Okay, because they will not react with the equal rate. Okay, suppose in this only we take one example as say hydrogen plus oxygen. They are combining to form water. Okay, they are combining to form water which is in the liquid phase. In this case you have the delta H value as minus 285.8 kilojoules per mole. This much heat is liberated. If the same reactant you are using, if you are using the same reactant, say water is formed and which is in the gas state, then in this case the delta H value is minus 241.8 kilojoules per mole. So the heat change will vary if the product form, the physical state of the product form is changing. So it very much depends upon the physical state of the reactants and the products. Now allotropic form. Allotropic form means, suppose I take one particular example of say carbon. Carbon in the diamond form or carbon in the graphite form is undergoing combustion. Combustion means they are reacting with oxygen and both will definitely form carbon dioxide, and both are combustion means obviously the delta H value has to be minus. It has to be minus. So in diamond the value is 395.4 kilojoules per mole, and if we are talking about the graphite, the value is 393.5 kilojoules per mole. That means the allotropic form changes, the heat of enthalpy, the enthalpy of the reaction or the heat of the reaction also will change. Allotropic form also modifies it. And the another 3 factors are the temperature, pressure and concentration. At what temperature we carry out the reaction, what is the pressure at which we carry out the reaction. So that also will define what will be the delta H value. There are some endothermic reactions, exothermic reactions, or the coefficients in the reactants are changing, number of moles are changing. So accordingly the enthalpy of the reaction will be changing. Right. Now moving on to the another topic, that is a standard enthalpy of reaction. How do you represent standard enthalpy of reaction? Delta H naught. Delta stands for change, H stands for enthalpy, naught stands for standard. Standard means the enthalpy of the reaction which is measured under standard conditions. The enthalpy change which is measured under standard conditions. Standard conditions means 25 degrees Celsius or 298 Kelvin you can have. In terms of the pressure, we say 1 atmosphere or 1 bar pressure. I hope this point is clear. The standard enthalpy of the reaction is defined as the enthalpy change that is taking place when all reactants and products are in their standard states. They are in their standard states. Standard states means what is the state at 25 degrees Celsius and 1 atmosphere pressure. Under these conditions, the standard states we have to talk about. For example, if I say water, the standard state under this condition of water is liquid. bromine is liquid, iodine is solid. Okay, then you have chlorine, you have chlorine. These are gases. These are gases. Okay, for sulfur S8, and that is the standard state of it, that is solid, right? You have phosphorus P4, that is also solid. So the standard states are these. What are these states? The enthalpy changes which are taking place in the reaction when all the reactants and the products are taken in the standard state. And the standard state means under this condition, temperature and the pressure has to be specified. Okay, and we represent the standard states as delta H naught. Naught value we can write down. Fine. Now moving on to the types of enthalpies of reaction. Enthalpy of combustion. How we define is amount of the heat liberated. I already told you combustion is always exothermic. It is always exothermic. The amount of the heat liberated when 1 mole of a substance is burnt completely. This is very important. Burnt completely in the presence of excess of oxygen. 1 mole should be burnt and 1 mole should be burnt completely also. For example, if I say carbon has to burn, carbon plus oxygen, if the equation says it is forming carbon monoxide, this is not enthalpy of combustion then. It should be burning completely. Burning completely means it should be reacting with oxygen and it should be forming carbon dioxide. Carbon dioxide. Because in this case, if I am taking the delta H value which is given out as 110.5 kilojoules per mole. Whereas if I am taking here the delta H value, that is the enthalpy, is 393.5 kilojoules per mole. This is the enthalpy. So enthalpy change is different here. So this is very, very important. 1 mole should be burning completely in the presence of excess of oxygen. Not partial combustion. Partial combustion is not said to be the enthalpy of the combustion. Fine. The similar equation can be written with any substance which is to be burnt. Suppose we want to write down the enthalpy of combustion for hydrogen. You will write down the equation like this and it will be forming water. And to balance it, you will always keep in mind whatever substance is burning should be 1 mole. So you will balance equation in such a manner that whatever substance is being burnt should not be changing in the number of the mole. That should always be 1 mole. Suppose we have to write down the enthalpy of combustion for methane. It can be the same equation which we wrote over here. We wrote this equation over here. That is methane combustion. That can be considered to be the enthalpy of combustion of methane. Fine. Now suppose if the enthalpy of the combustion is to be measured under standard conditions, that is 1 atmosphere and 25 degrees Celsius, then it will be called as standard enthalpy of combustion. How do you represent it? Delta for change, C for combustion, H and then naught. Okay, like for example, this is given here. Butane undergoes combustion and it is forming, any hydrocarbon will surely form carbon dioxide and water. So this will be called as the standard because under standard conditions it is given. This is liquid, this is gas, this is gas, this is gas. Okay, now something related to the hydrocarbons or any kind of the fuel, you can also define calorific value. For example, the definition is amount of the heat produced from complete combustion of 1 gram of the fuel. 1 gram of the fuel, to burn 1 gram of the fuel, what is the heat liberated? That is called as the enthalpy of, that is called as the calorific value. For example here, butane. You know butane molecular mass is 58. So 58 gram is being burnt here. To burn 58 gram, the heat liberated is 2658 kilojoules per mole. Kilojoules per mole. So what will be the heat liberated to burn 1 gram of the substance? You will have this as 2658 divided by 58. Did you follow? So this will be 45.8 kilojoules. This will not be per mole now. This will be per gram. Calorific value is always per gram. This much kilojoules per gram. The unit can be according to what is given. So this much kilojoule per gram it will be. Calorific value. and more the calorific value means more is the amount of the heat produced by that particular substance. Clear? For example, you can see in this tabular column they have given the calorific values of the different substances. Okay, so whichever substance is giving more amount of the heat per gram, that will be said to have a better fuel. Fine. Moving on to the next enthalpy, that is say enthalpy of formation. We will represent like that delta HF. So the amount of the heat change. Heat change because it can be endothermic or it can be exothermic. Amount of the heat change taking place when 1 mole of a substance is formed. In combustion, 1 mole was burning. In this, 1 mole is formed from its constituent elements in the standard states. From the constituent element, not that any particular method of the preparation we will be considering. For example, we have to form ethanol, ethyl alcohol. Now, ethyl alcohol is in the liquid state. This is to be formed from the constituent elements. What are the constituent elements present in it? Carbon is one element. Another, hydrogen. Hydrogen exists as H2. So, we will write down H2 only. Plus oxygen. That is also existing as a gas. So, this is gas O2. This is also gas H2. This is solid carbon. So, this is 1 mole to be formed. So, when you are balancing it, you have to keep in mind that whatever substance is being formed should be 1 mole. So, you will write down 2 here. To balance it, this will be 3 and this will be half. This is the enthalpy of the formation. And whatever is the heat liberated, you don't liberated or absorbed, you don't have to remember the values here, ki this is minus or this is plus. While looking at the equation, you should be able to judge whether it is endo or exothermic. If suppose in the formation of the compound, the heat is liberated. If the heat in the formation is liberated, the compound so formed will be called as exothermic compound. If in the formation of particular compound the heat is liberated, it will be called as exothermic compound. If in the formation of a particular compound the heat is absorbed, then the compound will be called as endothermic compound. By again looking at the equation only, you should be able to judge it whether it is endothermic or exothermic compound. The same thing, if we measure under standard conditions, we will represent this as standard enthalpy of formation. We will just put that not value, not on the top. That means under the standard conditions, the value is given. Most of the times we write down, we represent it always in form of the standard enthalpies only. Okay, now whatever is to be formed should be 1 mole as I said. Suppose we have to write down for the formation of HCl. What are the constituent elements? H2 and Cl2. This will be in the gas state. This is the standard state of chlorine. This is the standard state of hydrogen. This is the standard state of HCl. And to form, this should be 1 mole. Because in that process only we say it is enthalpy of formation. So to balance it, you will make it this half and this half, not this 2. At times for two HCls, the value was given. Then what will be the enthalpy of formation? You will not call that as enthalpy of formation. In that case, you will be dividing by 2. For example, if I say N2 plus 3H2 and it is giving you 2NH3, this is one equation given, and for that the delta H value is some minus X kilojoules per mole, whatever. Some value is given, X kilojoules per mole. What is enthalpy of formation of ammonia? If for 2 moles this value is given, the enthalpy of the formation of ammonia would be then X by 2. Because for 1 mole formation we have to see the enthalpy. That is called as the enthalpy of the formation. Clear? At times you are given the enthalpies of formations of all the reactants and the products. Of all reactants and products, and you are asked to calculate the enthalpy of the reaction. Then how will you do it? Suppose this reaction is given. This reaction was given, N2 plus A. Enthalpy of formation of all were given. Then how will you do it? You will have the formula. Enthalpy of the reaction will be equal to standard enthalpy of the reaction. Will be equal to sum of enthalpies of the formations of the products minus sum of enthalpies of the formations of the reactants. that will be called as the enthalpies of the reaction. At times these type of questions are there where the enthalpies of formations of the products and the reactants are given. You will just do the addition of the products and the reactants, you will get the answer, right? See, in this question you are having enthalpy of formations are given for all the reactants and the products. So the enthalpy of the reaction is sum of the enthalpies of the formations of the reactants and the products. And on the top also you can see some physical states are there. The standard states, for them the enthalpies of formations are always taken as 0. Clear? Please take the screenshot of it for making the notes. Moving on to the next enthalpy, enthalpy of neutralization. This is also always exothermic. Amount of the heat liberated when 1 gram equivalent of acid reacts with 1 gram equivalent of base. This is one definition. Or it can be to form 1 mole of water from H plus and OH minus ion. How much heat is liberated? That liberated heat is called as enthalpy of neutralization. Clear? So in the formation of 1 mole of water, the heat liberated is always this much, minus 13.6 kilojoules per mole. Or instead of this, we can write down in joules also, kilojoules also, this much kilojoule per mole. So either way we can define it. Now let us understand what is the meaning of that statement, 1 gram equivalent. And why 1 gram equivalent was required, not 1 mole in this case. Suppose I take the example of some base which is giving 1 OH and acid which is giving 2 H plus. It will be reacting and forming the salt and it will be giving 2 moles of water. In this there are 2 moles of water formed. So there is nothing standard like 2 moles of water will not be giving this much amount of heat because we fixed it for the formation of 1 mole of water. So if you divide this by their acidity or the basicity, we are converting them for 1 gram equivalent. This is definitely giving. So balancing with this will be 2. In fact, that I did not do. So if this is giving 1 OH, otherwise without balancing, this is giving 2 H plus. So that will not be surely forming 1 mole of water. It will be forming 2 moles of water. So to have it, fixed, we say 1 gram equivalent of acid and 1 gram equivalent of base. How much heat is liberated? That is called as enthalpy of neutralization. Very important thing here is, suppose you have some reaction of strong acid and strong base. The enthalpy of the neutralization is always minus 57.1 kilojoules per mole. That is always fixed. Because if it is strong acid and base, both will be giving H plus and OH minus ion and both will combine and form water only. So that much heat is common whether you take one acid or another acid. But if you have weak acid, strong base, or strong acid, weak base, any one is weak, or you have both weak acid and weak base, then in all of these the enthalpy of the neutralization will not be equal to this. It will be lesser than this. It will be lesser than minus 57.4. Why it will be lesser? Because if any acid or base or both are weak, some amount of the energy will be required to ionize the weaker acid or base. In such cases, for these cases, the enthalpy of the neutralization for them would be equal to minus 57.1, which should have been liberated, plus enthalpy of ionization. Enthalpy of ionization for the weaker acid or base. Whatever acid is weak or base. Is this point clear? How much energy is required to ionize will be endothermic. So the liberated automatically will be less. For example, I say for weak acid. Okay, for the first example, if I say the enthalpy of ionization for the weak acid is 1.2 kilojoules. What will be the enthalpy of neutralization for this acid? Minus 57.1 plus 1.2. If I take another example, say strong acid HCl and I am taking weak base ammonium hydroxide. And I am telling you the enthalpy of ionization for this weaker acid is given as say 2.1 kilojoules. This much energy is required to ionize it. What will be the enthalpy of neutralization for this particular? You will say enthalpy of neutralization for this is equal to minus 57.1 plus 2.1. So you can just do that and you will get the answer. That will be the enthalpy of neutralization. I hope the concept is clear to you. Now children, if you have followed the various enthalpies of the reactions which we have done so far, you also will be following this easily. So for last 2-3, we'll just do the definition part. The other thing you can, understand accordingly. The first one says enthalpy of solution. Enthalpy of solution, just read the definition first. Amount of the heat change. Heat change means can be endo or exo. When 1 mole of a substance is dissolved in so much excess of the solvent such that further when you add the solvent, there is no more heat change taking place. For example, I take KCl, some solid I have taken KCl. And if you dissolve this solid in water, aqueous means water, if you are adding water, go on adding water to it. You have taken 1 mole, that is fixed. Something has to be fixed, no? So 1 mole is fixed. If you take 1 mole of that potassium chloride and add water to it, there will be heat change. Go on adding water, there will be heat change. That much excess solvent if you add, such that by further addition of the water, there is no heat change. That will be called as the enthalpy of solution. So the product form will be aqueous solution of KCl. Okay, in that process, how much heat is evolved or absorbed? Anything it can be. That depends upon what reaction you are talking about. It can be endothermic or exothermic. So the enthalpy change which is taking place. In this case, the enthalpy change is plus 18.6. This is endothermic reaction. 18.6 kilojoules per mole. In certain cases, energy can be liberated also. But the concept is clear, I suppose. When you dissolve 1 mole of a substance in so much of water, such that by further adding water, there is no heat change taking place. Now, something similar to that is hydration. Normally, children get confused. This is saying amount of the heat change taking place when 1 mole of anhydrous salt, let us take copper sulfate, so 1 mole of anhydrous salt combines with required number of water molecule. Required molecule for every salt is different. Suppose copper sulfate, if it is combining with 5 water molecules, anhydrous copper sulfate is combining with 5 water molecules and it is forming copper sulfate pentahydrate. In the process of formation of the hydrated salt from the anhydrous salt, what is the heat change taking place? That is called as the enthalpy of hydration. For example, in this case, it is minus 78.2 kilojoules per mole. This is in terms of delta H written. Okay, for every substance, it will be different. If you are taking ferrous sulfate, for ferrous sulfate anhydrous, if you add 7 water molecules to form a hydrated ferrous sulfate, that is with 7 water molecules, what is the heat change taking place? That will be called as the enthalpy of hydration for ferrous sulfate. That varies depending upon what compound you are taking, what type of the salt you have taken. Okay, this was enthalpy of hydration. So this is the 5th one we have done. Enthalpy of combustion, formation, neutralization, solution, hydration. Enthalpy of atomization. Enthalpy of atomization says when 1 mole of a substance dissociates into gaseous atoms. This is 1 mole of H2 dissociates into gaseous atom. What is the enthalpy change accompanying it? Okay, what is the enthalpy change accompanying? So most of the time this is endothermic. Energy will be always required to break the bond. Okay, so H2 to form 2H. This is in the gas state. Also in the gas state, what is the enthalpy required? You will represent like this if it is standard enthalpy. Standard enthalpy of atomization. Whatever the answer is, the value is. Same way methane, if methane gas, we have to convert to carbon gas and 4 hydrogen, all 4 bonds to be broken down. What is the enthalpy required? That is enthalpy of atomization. Okay, same way, it can also be considered as some solid converted to gas. Sodium solid when converted to gas. Any solid, you can take carbon solid converted to carbon gas. That is also enthalpy of atomization. Right? Now, the next one is enthalpy of allotropic transformations. That means the amount of the heat change taking place when 1 mole of one allotropic form changes into another. One allotropic form is changing into another, that is called as the enthalpy of allotropic transformation. For example, carbon in the graphite form, say, changes into carbon in the diamond form. This is called as enthalpy of allotropic transformation. Sulfur in the monoclinic form is converted to sulfur in the rhombic form. The enthalpy will be called as enthalpy of transformation. These you will be using, in case we apply Hess law of constant heat summation, we are not able to calculate some of the enthalpies, so then we can make use of this. Fine. Now, at the end, we will just discuss these enthalpies. So, definitions, I think you can write down on your own also. It is something like this. First 3, these are all endothermic. These are all endothermic. This depends. The bond is being formed. So this is, sometimes, most of the time liberated for the last one, or it can be required also. Now just see, what is enthalpy of, this is enthalpy of fusion, vaporization, sublimation, hydrogenation. 1 mole of solid is converted to liquid. What is the enthalpy required? That is enthalpy of fusion. 1 mole of liquid is converted to gas. Enthalpy of vaporization. 1 mole of solid converted to gas, enthalpy of sublimation. 1 mole of unsaturated hydrocarbon is converted into saturated hydrocarbon, means 1 mole of H2 is added on. What is enthalpy change taking place? Then that is called as the enthalpy of hydrogenation. Okay, so please learn all these enthalpies, because in the next part of the chapter, that is the Hess law of constant heat summation, we know some kinds of the enthalpies and we are not able to calculate some other forms of the enthalpies of the reaction, we can calculate, applying the Hess law of constant heat summation. But to understand that concept, we should be knowing all the types of the enthalpies properly. So please learn these well till then. Fine? Thank you.